While waiting for the rest, think about the series whether it converge or not. Uh, Maybe we wait 2 more minutes. While waiting, you can think about whether this series converge or not. Okay, so what do you think about this series of adding natural number? The converge or diverge? Many tests you learn already. As for divergence, P series, and then sorry, comparison. Okay, comparison test, simple comparison test, uh, limit comparison test, integral test. Use any test of this series or not? Test for divergence. So what do you get if you want to use test for divergence? What do you compute first? Huh? You compute the limit of an. What's an here? This is a calculus 2 class. Are you for calculus 2? What's your name? Virginia. Okay, yeah, this is your class. So what's the limit of an here? Limit of n. Okay. So what's the limit of n here? Obviously infinity, which is not 0. So by test of divergence, the series diverges. But the meme said this answer equals to negative half over 1 over 2. Have anyone seen this meme on internet before? Got some of you got. Okay. Why? Is it possible or not? Yeah, is it possible or not? So if you try and play around three series here, A, B, C, you suppose them converge to some number. Then you play with a little bit of infinite calculus or algebraic operation here. Then you will get that it is really equals to negative half. Okay, I won't go through this, but I will pause it up if you are interested. This is what we call the Ramanujan summation. This is what the Indian mathematician Ramanujan did. Okay, that time I think is there a computer yet? Maybe there is, but very primitive one. Mostly he calculated on his notebook, and then he has a pile of notebooks. Ramanujan. So but if you similarly did something kind of reasonable, but is it how does it portray in our physical world? Does it has any meaning or not in our physical world? Okay, it turns out that there is an application of this negative 1 over 12 in our physical world. In particular, when we look at the quantum world, okay, in particular, we look at the quantum physics. Okay, so what's the quantum physics involved here? This is what they call the Casimir effect. Okay, Casimir effect. So if you can imagine, you take two plates, okay, that has the same charge. So they will, how to say, same charge you learn in the physics. What happened if they put together? They repel. Okay, so you can imagine this 1, 2, 3, 4, 5 is the repelling force. So when you push two plates closer and closer and closer, so the repelling force will add up and add up and add up. But a very intriguing phenomenon happened when you push them really, really, really close. And you know what happened? Stick together. After they pass a really, really small distance, they turn to stick together. So that's why the effect becomes negative. So this kind of calculation has a meaning in the quantum world. So similarly, the assignment I set to you, the question two or question three? Three, huh? You know which question I'm talking about? 庄子, huh? Okay, the 庄子 one. Right. Okay, the 庄子 one. So you cut. Can you keep cutting your I translate into ruler, right? So can you keep cutting the ruler or the wooden stick infinitely many times or not? What happened? Okay. But first half, of course, uses the knowledge in our class, but second half of the question is an open question. So you can answer with your viewpoint, okay, toward this word. Or you can do some research. And the second part is a open question. Okay, but first part, you need to use what we have learned, either sequence or either series. Does that make sense? Okay, so another thing about your assignment, if you say you go and search a different way from what we learn in lecture notes, you're not sure, come and ask me first whether you can use it or not. Okay? Come and ask me if you are not sure whether you can use something outside the lecture note. If I say cannot, go back lecture note and find, then you need to use what? Okay, so this one is extra knowledge. So I think I don't suggest you. Maybe you can. Maybe if you want, you can see if there's any theory on this from Ramanujan summation or not. If for my knowledge, I didn't find any. So if you have found some rigorous theory about Ramanujan summation, you can do it in your project one. But this application, physics application, is very good title for your project two, apply project. Okay, how to apply series into quantum physics. Okay, so project two is an apply project. Okay, yeah. Right, so any question from last lecture? Have you tried out the exercises yet? Left last time? If you try out, do you met any difficulty or not that you want to ask? So far, okay or not? Please, you have to go back and do the homework that I left to you, because that's how you get familiar with these mathematical objects. Okay. If you miss a lot, if you just want to pick up in during the midterm, I think you will get much suffering. Okay, so suffer first before too late. Yeah, don't cram everything to the end. Do it bit by bit. Okay, if you don't have question, then we'll continue. So next we'll continue with alternating series. So what's alternating series here? So you already seen alternating sequence, right? 1 minus 1, 1 minus 1, 1 minus 1. So this time we're gonna add them out. Okay, we're gonna add them out. So we'll define what is an alternating series first. So an alternating series is a series of the form B1 minus B2 plus B3 minus B4 plus B5 minus B6, where Bn is greater than 0. Okay, so we require all here the Bn is already positive. Okay, then I add the alternating sign to it. So what's the example? So whenever I put these symbols, right, you need to have examples in your mind. What sort of example you could have? Sum of alternating minus 1, for example. Okay, so what do you get is 1, sorry, minus 1 first, right? So to make it the same, maybe we take minus 1 to the n plus 1. So we'll have 1 minus 1. The correct or not? Yep. Plus 1 minus 1 plus 1.
That's all. Okay. Okay, so it's an outer series.
So for this kind of special alternating series, we have a test also. Okay, we have a test. Okay, the mic a bit lasting.
So let's write down what the alternating test is. Alternating series test. Okay, so if the alternating series satisfies two conditions, okay, satisfies two conditions. Bring this down. So let's bring this down. Right. So sum from where to where? So you have b n here, okay, and then you have minus 1 to the starting from 1, so you need n plus 1 infinity.
So two conditions here. So first of all, you can imagine you have a series, right? Okay, you have a series. When you add these terms together, what the series has to satisfy to converge for the series? What these terms have to satisfy? How do you start imagine? You need to always start with one example first. Okay, you cannot just imagine blindly, abstractly. Every abstract thing, right, comes from practical things. So you need to imagine very easy series first. For example, what? Yu Liang, can you give an easy series? Start somewhere. Anything. What do you think? Any series. So you want to add all the odd number together. Again, let's say you want to add all the odd number together. You see that it diverge or not? 10 or not? 1, 3, 5, 7, 9. Can you see that it diverge or not? How to see? That's for divergence again. Correct or not? Okay. But if you really look at the sum itself, right, what happened? Every time you add, what happened? For every partial sum, what happened? 1. 1 plus 3. 1 plus 3 plus 5. 1 plus 3 plus 5 plus 7. What happened? Each time you add a larger and larger number. So obviously the series will grow, right? So if you want the series to converge, what do you need to impose to this series? Minus, maybe you want to take away, right? Okay, maybe you want to take away. So take away will do what? Make the figure smaller. Okay, so maybe let's say we don't take smaller and smaller, just constant is enough or not? 1 plus 1 plus 1 plus 1 plus 1 plus 1. Every turn stay constant. Is it enough for series to converge or not? No, right? Still diverge, right? Because you still have a constant growing. Okay. But even I make it smaller, 1 plus half plus 1/3 plus 1/4 plus 1/5. Converge or not? Still don't converge or even I add every time smaller and smaller amount. So how small I need to add so that this series converge? This is very important question in this topic here about convergence series. Okay, so in this case here, so first condition you need to satisfy obviously is the term have to be decreasing, at least decreasing. But how fast it decrease?
Okay, but how fast it decrease? Second condition, you require that the limit of Bn goes to 0. So if these two put together, then the series converge.
And you might ask, if you just look at these two conditions, harmonic series also satisfy it. Correct? No? Harmonic series, every term is decreasing, limit of each term also goes to 0. But it doesn't converge. Okay, it doesn't converge. So the key point here is alternating series. So you add alternating sign to it. Okay. Okay, you don't just add all the terms together. For alternating term, you take away.
Yeah, take away something from this um, series here. So, can you imagine what happened? Can you draw this phenomenon in picture or not, or geometry? Okay, so one trick in calculus, you need to think of numbers, right?
As a distance. Okay, distance of some line. Okay, so if I say 1, you should think of a distant 1 line. Okay, so 2, then you need to think of distant 2 line. Okay, this is very different from algebra. If you study algebra, right, what do you think about 1 and 2? You think about 1 as one thing, one discrete thing. 2, two discrete things, maybe 2 bottles, one student. But in calculus, you want to think of 1 as comprising everything, okay, from 0 to 1. No, no, a line. Okay. So, so what happened to this Sn? Can you imagine? So let's start with 0. Okay, let's start with 0. So we assume that Bi are positive, right? Okay, if you look at S1. Okay, so what is S1 here? S1 is simply B1. Right or not? Okay, it's just simply B1. So let's draw something like this. B1, which is S1. Okay. What happened to S2? S2 is B1 minus B2. But minus B2, how to draw?
B1 minus B2, how to draw? So you have B1, and then you take away B2. But how far you take away B2? How far? Can I go super far? How far? Think so. Cool, right? Smaller or equal to B2. Sorry, B1. At least as far, sorry, at most as far as B1. Okay, at most as far as B1. Okay, so I think I put B1 here better. At most B1. Okay, at most. So maybe we draw some schematic representation like this. Okay, so here is S2. How about S3? B1 minus B2 plus B3. Okay. How about B3? Can I go super far or not? Cannot. Where can I go? Not too far again. So how far? Huh? How far? How far? Right. About Huiqi. How far can I go for B3? Okay, so I'm adding B3, so I need to go to the right, right positive. How far can I go? Huh? More? 不知道。OK，谁知道救救他一下。At most B2. Okay, because you need to read from here. This inequality here is true for all n. So meaning what? If you write, so this implies what? B1 will greater equals to B2. B2, and then B2 will greater or equals to B3. So you see B3 is at most B2. Okay, you cannot go further than B2. Okay, so maybe we draw some schematic picture like this. Cannot. Okay, make sense? Get it? Okay, so what can you imagine? So you can imagine that the sum of will go back and forth around a point, actually. And then eventually it will converge to one point. Okay, so this is the idea. Okay, this is the idea. Okay, you can try and prove it. This is the idea. Is everyone getting this? Does it make sense or not? This one minus, this one plus, this one plus. Does it make sense? Okay. 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 So let's see. Let's see. What should we do now? So let's try and use this. Okay, let's try and use this. So this next is a very important or classical example for this alternating series here. So we will show that the alternating harmonic series converges. So we won't prove the test. You can prove it in your project. So if you're wondering how to get the difficulty marks in your project, right? All those that I suggested are possible to get high marks. Because as long as you're filling the gap that I didn't do in class, that prove that you did something extra outside this class. Then this something extra is the difficult part. Okay, the point of project is what I want you to do something extra from this class. Okay, show that the alternating harmonic series is convergent. So what do you need to do? So first, you need to check what? Whether Bn is decreasing or not. Okay, is it decreasing? Okay, is it decreasing or not? So what's our Bn in our case? Let Bn be. What's our Bn? You know? Huh? What's Bn here? Bn is something such that B1 minus B2 plus B3 minus B4, right? So what's the formula for Bn here? 1 over n. Correct, no? Okay, 1 over n. So you should look at the positive part. 1 over n, right? 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7. Okay. So this means that what do you need to verify here? You need to verify that for all n greater or equals to 1, 1 over n is greater or equals to 1 over n plus 1. Is it true or not? This is true if and only if what? N plus 1 greater or equals to n. Cross multiply, right? But when is this true? Hmm? When is this true? Did I did something wrong or not? N is n plus 1 greater or equals to n. When is it true? It is true when 1 is greater or equals to 0. But 1 greater or equal to 0 is always true. Obviously, equals to 0 is not true, but this is a statement of all, right? To have 1 greater than 0. Okay. True or false? True. The statement is still true. Okay. So since we have 1 greater than 0. Okay, so it's always true. Okay. Good. And then the next thing we need to check is what? We need to decrease fast enough. So we need to check that the limit of Bn is equal to 0. But this one is obviously true, right? From the sequence calculation, limit of 1 over n is simply 0. Okay, so you can conclude by the alternating series test that the alternating harmonic series converges. Okay, so this one is a very important example to keep in mind. Okay, right. Any question or not? Any question? Yes. You mean like alternating series test like that? You mean harmonic? Which one? If it is clear from context, you can. Yeah, for example, you already demonstrate alternating series test condition already. For sure, I know you want to use AST, but sometimes it appear out of nowhere, A dot ST, S dot T dot. Then what do you expect me to know about that thing? So if you like, for example, already doing some checking on this AST condition, then if you use AST, then I can easily get what you want to do. Okay or not? Yeah. So short form is created to make people life easier. Again, not make people life confused. So if you think it make it easier in this case, then you do it. If you think that it make people confused, then don't do it. Simple reason. Okay. Yeah. Although I do this short form because I want to save time writing. Okay, so if no question, how about let's do some exercises. So let's try. I give you some times. I give you 5 minutes. Let's test. Let's do 2 exercises. So first, let's check this series. So this is the sum of the alternating 1 over n factorial. Okay, and then the other one is this. Okay, so check their convergence. Check whether they converge. Okay, so you can see that these 2 series are tailor-made. You know what tailor-made is? Do you know tailor-made? You know what happens if your shirt is tailor-made, custom-made, or tailor-made? 量身定造. Okay, we have to measure your body first. Measure your arm length. Measure your chest length. Okay, so this one is exactly alternating series. Okay, so try and use alternating series. Okay, is it halfway done? Halfway done? Maybe you can start first. Okay, for the first one, I think for the first one is quite straightforward, right? Okay, so for the first one, quite straightforward. So what do? So you set your Bn first. Okay, what's your Bn? Okay, Bn is the part that's not alternating, right? So it is just 1 over n factorial here. Okay, so um, so you need to check that whether 1 over n factorial is greater or equals to 1 over n plus 1 factorial. Okay, but when is this true? This is true when n plus 1 factorial is greater or equals to n factorial. But is this true or not? This is true when n plus 1 is greater or equals to 1, which is when n is greater or equals to 0. But what you care is n is greater or equals to 1. Okay, so it's always true. Okay, sense? Okay. So which is, so I will say that which is true as n is greater or equals to, which is greater or equal to 0. Okay, and what else? What else you need to check? You need to check that it actually decreasing fast enough. Okay, how fast? Just make sure it converge to 0. Okay, but we know that limit of 1 over n factorial goes to 0. Okay, so by AST again, okay, by AST, the series, the alternating series, converge. So for the second one, a bit trickier. Can anyone try how to show this decreasing or not? What do you do? What's Bn here? N square over n cube plus 1. Okay. Then what do you do? Is it similar thing? Do you do the similar thing? N square over n cube plus 1 greater equals to n plus 1 square over n plus 1 cube plus 1. Did you do this? Anyone do this? Xiaoben, what do you do? 求导. Oh, 求导. How about the other? What do you do? 恩慈, what did you do? What did you try? This one, 睁开来. Did you get anywhere else? Not yet. No or not yet? Let me see. Okay. And this one quite confusing, huh? Okay. Um, I'm not sure. Maybe you can do some estimate, but I haven't tried that way. How about the rest? Also open up. Boom ping. What do you try? Oh, mathematical induction. Have you finished trying or not? Mathematical induction. So let's see what the base case are. So base case is 1 over 2 on the right hand side. The other side is 4 over 9. So it's 1 over 2 greater or equal to 4 over 9. Yeah. Okay. So maybe you can try mathematical induction. Maybe. How about the others then? Other than these two, did you try any method? How about I get some voice there? 子莹 是子莹吗？子莹. What did you try anything? No. No. Okay. Humble. Oops.
change the first one to 1 over n plus 1 over.
Which first one? Left hand side, right hand side?
Both.
Both. Okay. What do you do? Divide.
Divide. So upper side and lower side.
Okay.
N square.
N square. Both of both sides.
Second one is.
So you mean like this? How about the other side? Keep the same. Okay, sure. 1 over n is 1 plus 1 over n plus 1 square like this. Very obvious.
How obvious is it?
1 over n is more is less than 1.
Oh, wait. Let me write down what you say. So we know that 1 over n squared is always greater or equals to 1 over n plus 1 square, is it? This is what you mean?
Is 1. 1 over.
Which one? So what do you want to compare first?
Square.
Yeah, 1 by N square.
And 1 1.
Ah, okay.
So you mean you compare this one and this one? Okay, so you get like this, is it?
Okay, and then so N and N is the same.
So you add n to both sides, is it? Like this? Okay, and then so because it's less than equal, so you can add more stuff, right? So this one is less than or equals to n plus 1 plus 1 over. Because 1 over n plus 1 square is positive, right? Okay, and then you can invert them. I think quite good. Good, quite good, quite good. Good. Yeah. So we get what we want, right? Okay. Right. Good. I think this one quite clean, this solution. Yeah. Everyone can see or not? Okay. Yeah, quite clean, I think. Yeah. But Nzi method also okay, and Yin method also okay. Okay. So you need to finish your work. But for Nzi one, I think you need to go to algebraic geometry. Because a bit complicated, that thing. Right. The power is too high. Okay. Right. So this is one way. But Xiao Peng said you can differentiate. Okay, so what are you differentiating? What are you differentiating? Here only have sequence. How can you differentiate? Hmm? So again, now we can see, so this one is the first method. I'll just leave it here, first method. So how about second method here? So we can look at the sequence, the function defined by this sequence here. Okay, we replace the n by real variable. Okay, in this case here, you can see that it is differentiable. Okay, differentiable at most places that we want. Okay, so if you differentiate it, what do you get? It's also a little bit complicated, but um, let's quickly compute this. And please check out the calculation. You will get something like this. Okay.
so if you notice what happened to this number here? So when you study calculus or analysis, right, you need to be sensitive to this kind of square number. Whenever a number is square, what do you get? Positive. Okay, so no matter what you put inside this bracket here, this bracket here, it's always positive one. And then the top here, okay, what happened to the top here? You will notice that this quotient here is less than 0 whenever s is greater than cube root 2. Can you see or not? See it? So if you plug any number greater than cube root 2, this number is positive. X is positive, right? But what happened here? What happened if you plug something greater than cube root 2? If you cannot imagine, you imagine cube root 2 first. So if you plug cube root 2 in, what do you get? 2 minus 2, 0. But if you plug in more than cube root 2, meaning what? You produce a larger number here. So you take a difference between smaller number and a larger number. So you get negative always. Okay. So if you see that this function is decreasing, right? The function defined by this sequence is decreasing. It also implies that the function that restrict to just natural number is also decreasing. So this is what we use here. And this is your assignment question. You need to prove it. Okay, but to prove it, I give you the hint already. Did you learn mean value theorem in your first semester or no? Yes, okay. But I don't require you to prove that. You just need to use it. Okay, just use it on. Okay, so you need to use mean value theorem to prove it. Why function decreasing imply the sequence decreasing. Okay. Okay, good. I think humble way is quite clean. You guys can try and learn. Yeah, very clean. Good. So mathematics, a very important principle is called 化繁为简. Then 化繁为简. Turn the complicated one to less complicated. 化繁为简. But this second method, why we introduce, we want to tell you there's a relation between functions and decreasing function and decreasing sequence. But in this case here, I also don't like this calculation. Long. You need to use quotient rule. Yeah, I prefer this divide, then done. Divide, compare done. Yeah. Okay, good. So I think the second condition is easy. What's the second condition here? You simply compute the limit of n squared over n cubed plus 1. Okay, so I think this one should be okay, right? So you divide n squared on both sides. N or n squared? N cubed. Okay, divide the largest one. Largest power. So you get 0. Okay, so by what? So here, be careful. Which term is this? Actually, which term is this happening? Decreasing. Which term is it? What is square root? Cube root 2. What's cube root 2? Need to be careful a bit. What's cube root 2? What's cube root 2? What's cube root 2? You can press your calculator. What's that? What's cube root 2? 1.26 something, right? So meaning this is decreasing after this point, right? Okay. So we only have decreasing like at n greater or equals to 2. Okay. So really, we only can conclude that by AST, what happened? The sum from n equals to 2 converge.
But are we still okay or not? Because we want to check starting from 1. Does it still converge? Why? You just add another term. Because this term is equal to some finite number. If you add one extra term, it is still a finite number. Still converge. Okay or not? Okay. So that's like what we said last time, right? Finitely many terms you remove from the convergence series, you won't affect the conversion because you just add it back. Okay. So since finite terms won't affect the convergence, so what do? We just simply add the first term back into our series. Okay. They still converge. Okay. Any question? Got question or no? Okay. Okay. Right, before we break, right? So let's look at one more observation here. Okay, so we said that it lingering around this middle point. Let's call it X. Okay.
Did you observe anything or not? What if you take the distance between S and S1? It lies inside the distance of V1. But if you take the distance between S and S2, it also lies inside V2. And then you can keep going on. And then you observe a pattern, which is called the absolute value of x minus Sn is less than or equals to Bn plus 1. Actually stronger. Is it stronger? Yeah, actually stronger. Let me see. Actually stronger. If you take S minus x1, it's even stronger. It's smaller than V2. Then if you take x minus S2, it's within V3. Even stronger. Okay. So can you think about why? Why is it? Is it bounded by Bn plus 1? If you think about this inequality, right? It is claiming something quite strong, you know. Do you know what's S? S is an infinite sum. You sum everything. And then you take away a partial sum. Somehow only bound by one term only within that series. This is quite strong, you know. This bound is quite strong. Correct or not? Because if you imagine your series could add up a lot of terms, but still bounded by a finite term. And there's a formula for it. Okay, so why is this true? Why is this true? Right? Why is it true? I mean, you cannot just plainly think. You need to hands-on, try, compute. What is S minus Sn here? If you take away the partial sum already, what do you left? What do you left with? Huh? You can compute one. What does it left with? Left with what? What does it mean by there's an infinite sum, take away the partial sum? You start with what? Yes, you start with the n plus 1 term, no? Correct or not? You start with the n plus 1 term. And then you keep going on and on and on and on. Seems like I write something stupid here. It's true. I think it's n plus 1 here. Okay, so you go on. Okay. But do you know about this thing or not? You know about this thing? You know about some? You know something about this infinite sum? Don't look at me. Think. Don't look at me. Think about this picture. Think about this sum. So what can you take? What can you like? Take an example. For example, you take two, right? That B2 here, for example. Then you go B2, B3, B4 like that. From this picture, can you find any useful bound? Say for the two case. If you start with B2, then you go in, something, just so you stay within this region here. And then what's this region here? This region here is simply S1 minus S2. But is it true for other cases or not? If I start with B3 and then go the zigzag, is it between S3 and S2? Okay, so you need to prove, that this thing is less than or equals to Sn plus 1 minus Sn. But what is this? Difference between two partial sum, consecutive partial sum. You left with the last term. So what's the last term here? N plus 1. Okay. Yeah, so this is the key point here to see. Okay, so this is the key point here. Okay, so any question now before we break? So for some of the question inside the like the preview lecture notes, right? Some of them I skip. If you think that I'll tell you those I won't test, but some of them I skip, you can do it. If you think that you don't know how to do or you cannot learn it yourself, you can bring it up the lecture, then I try and discuss. Yeah. Okay, if I think it's useful. If it's not useful, then I'll tell you. No need to worry about. Kind of. Okay. So let's take a break until 10:11. Take attendance 啊。元语、川渝，sorry，川渝呀，天童、小鹏、金生、trade you，trade you，all you are trade you，呀，子怡、慈个、余光，哎，光个，Isaac 个，吴明个，春香个，玉良，威奇、海伦个，杨个。and 小莹，which one is 小莹啊？对，小杨呢？小杨 not here. Okay. 平一平 OK. 红杰 not here. 常云 I think not here. 俊彦 can you come here for a moment?
啊，但是其实你是可以先来上课的啊，因为不然的话你会丢掉已经两个东西了。这样的话你要补来或者我帮你补来。那已经在录了也长了，所以我建议你把我们的 recording 都开起来，不用每一个字看了，就是说重点你要抓一抓。OK，所以你上次拿给你课的那个经验是怎么样？你觉得怎么样？不太好，就是说一点都没学到，还是有些没
有些
做 sequence 这个课，
知道
然后或者是后面的，比如说 integral 还是 geometry，对，这个 integral 要画空间，那比较难的。OK，那前面那些 geometry equation 呢，画那种圈圈的那种，还好了，就后面那段就很难了。所以你看的那个 assignment。对，第二作业，你觉得你跟我说星期日目标是，所以能吗？我觉得应该可以啊。OK，所以我的课可能会比你跟你之前上过的越少，所以你要来上课，然后或者要来听我讲的那些东西，因为有时候我的重点是要来 OK，好不过不管怎样啊，就是你不会做的话，assignment 啊以后啊，你都可以来我的 office hour 或者问我或者 email。OK，然后我们 office hour 就是你有看到吗？周二的2点到4点跟周三的2点。然后在那里也有那些学长妹们在，就是拿过我课的，所以他们知道我要什么，他们可以干你要如果是这样，如果我呃如果周日可以教，那就周日，就周日。你有什么问题吗？有什么问题要问？没问题。呃，好的，这边 OK，第九个 squeeze theorem，然后呢，你要怎么用 squeeze theorem？我 BN conversion 零，先不用，这个不是我们要证明的东西。然后我们要证这个，也就是要证这个是成立的，然后要证这一个事情啊，这一个就证明这个 OK 好，对啊，这个不是极限不能够倒退嘛？squeeze 又不是后面去前面，我们 squeeze 是前面去。极限过后的东西被隐藏了，其实很长极限过后的东西都被隐藏，一节全部不见了，去极限过后。比如说一个 limit 去零，你怎么知道它 sequence 在哪里？然后那个 sequence 是到尾巴的时候是靠定的，但是前面怎么样我都不知道，或者中间怎么样我也不知道。对对对，也是。那个数值是打破。
这样子说来对了。Awesome. 应该是刚才是才顶过来的，应该拉不去了。这个起不来啊！是，然后你是的是这样，是不是把我啊？这也是一个知道，这也是没有昨天有吃饭吃。然后太兴奋了，啊，辛苦，老师我还有看到那个心情跳起来太兴奋了。对啊，对对，OK 啊，对。因为以色列没有进去打，有一起，没关系，我已经打算走，我也是没有，不要先例你打，你知道吗？新闻才出来，老师应该是太成奖，太成奖，对，没有新，但是新闻太慢出了，就新奇怪的那4点半，知道是吗？没有奇怪，很奇怪，因为圈是3的，突然间被中国点，第二天讲话脑干飞过去了，被讲话了是。然后你飞很多去，没有啦，上次才刚讲了。 这个月还有，好像是每个月都是吧？会再掉的，fat 每年定的，对他很贵，一学这个某大学的，对吧？还有有不能去啊？去哪里？这么讲，希望是以色列啊，我去不了，跑不去了。
Okay, so let's continue. Continue first, right? Continue. Okay, so next we'll talk about absolute convergence. So let's define does it mean by absolute convergence. So absolute meaning there's only one absolute, you know, right? Absolute value. So where do we put this modulus thing? So if a series n, okay, and the absolute of these series, okay, so meaning you take absolute value at every term. Okay? So what do? You make every term positive, and then you add them together. Can you imagine or not? You got an an, okay, maybe got a sporadic plus minus plus minus plus, or minus 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 plus plus minus. But now once you put this modulus, right, what happened? Every term become positive. So what you expect? You should expect that this sum of this modulus an should be larger, converge. that one was asking too much. So it might be larger sum than the sum of an. Okay, if both of them converge, okay, if both of them converge, we will say that the original one, okay, the original sum is absolutely. Okay, later I will tell you another meaning of this absolutely convergent. Okay, so if both of them converge, then it is absolutely convergent. Okay. So one example we can have here is, for example, you look at sum of 1 over n factorial. Okay, we have shown that this converge. Did we? Don't know. No, not yet, meh? Can we recall or not? I think I saw this before. Did we 1 over n factorial? Factorial. We do this or not? Over n factorial. If not, how to do this? 1 over n factorial. Will we use anything to show it converge? It's not a function, right? S factorial. Very weird. Then normal, then we need something else to show it. Okay, let's throw this example away first. Okay, let's don't talk about this example first. In future, maybe we can talk about it. The other terminology we want to introduce is if sum of an converges, but sum of absolute an diverges. Correct or not? Just now I said that this potentially produce a greater series, right? Okay, then we say that sum of an is conditionally convergent. Conditionally convergent. But this we have seen already. Can you remember what example fit to this conditionally convergent? I've just seen this alternating harmonic series. Okay, because alternating harmonic series converges. But if you take modulus, what happened to alternating harmonic series? It become harmonic series, but harmonic series diverge. Okay, so we will say that alternating series is conditionally convergent. Okay, so sometimes the question, when the question asks about convergence, right? Sometimes it will ask whether it is absolutely converged or not.
Okay, so if the question say, check the series converge or not. So you check whether it converge or not, and then maybe follow-up question says whether it is absolutely convergence. Okay, so you need to check what? You need to check that the absolute value of those terms also converge for the series. Okay, check two things, check extra thing. Okay.
Um, so so there's a very useful test here. It is called the absolute convergence test. Okay. So remember that I told you that if you put absolute value and potentially you create a greater series, right? So if these greater series converge, you should expect what? Expect your original series to converge also. This is a proof. I don't want to prove for you because the proof a bit dodgy, but I will show you the proof inside the lecture note, and then you should see why is it dodgy. Okay.
我这个人是很特别的啊，我对和错啊，我都要给你看，因为我要给你看什么是错。我不会只给你看对的东西吧，我要给你看错的东西，因为你要知道什么东西叫做错，明白吗？OK，不是说错我就要 avoid。It's not that it's something wrong I need to avoid it. No, you need to learn from mistake. OK，你要正面你的错误，正面你的缺点。Okay, you need to face your weakness, face your mistake. Okay, but you can do in your project. Okay, prove it.
MA1, we will do this in particular actually. Yeah. Actually, this testing is the last topic in your MA1. Every test appear in the last topic. Series appear in the last topic. Okay. So yeah, I want to tell you another meaning of this absolute convergence here. You see, absolute. There's another meaning for absolute. Do you know? English. Absolute. Absolute power. 绝对的力量，绝对。So if this absolute, I call it absolute series for the moment. If this absolute series converge, the original one also must converge. Very strong. So that's why we say that this original series absolutely converges. 一定要 converge 啊，管你做什么事情你都要 converge。你把全部辩证它都会 converge。OK， 它不辩证它也要 converge。Absolutely converge. Okay. Things to check. So two things to check, right? Absolute convergence. You need to check the original converge, and then the absolute series converge. So if the absolute series converge, already imply the original series converge. So the original series absolutely converge. Must converge. Okay, no matter how. Okay, good. So let's do it. Check on some example. So let's see how we use this. So let's see. Let's do on two example. So let's do this one and the other one. Okay. So shall we do it together? Let's do it together. So you want to show these two series converge. Obviously for the first one, maybe if you want to use AST, you can try it. Okay. So you can try. Actually, I encourage you for the same question, right? Try what series test can use, and then you compare which one is easier to use for this type of series. Okay, then you will build your intuition such that whenever you see the series, oh, this test, see this series, oh, this test, like that. Okay, build your intuition. So, okay, but now we are learning this absolute convergence test, right? So let's use that. So how to use absolute convergence test? Meaning, if you want to check these series converge, what do you need to check? You need to check their absolute value. Okay, you check their absolute value first. Okay, so let's make this question 1, this is question 2. So question 1, what do? You simply consider the absolute version of this series first. What's this absolute version of this series? This is simply what? Sum of 1 over n squared. What is this? This is simply p series 1 over n to some p. But this p is what? P is 2. P is 2 meaning what? It is greater than 1. So every p greater than 1, the p series converges. Okay. For p equal to 2 greater than 1. Okay. So by absolute convergence test, what happened? The original series also converge. Okay, so the original series converge. Okay, it doesn't just converge, huh? How it converge? Conditionally or absolutely? Absolutely. Okay, absolutely convergent. Okay, how about next one? Next one. So you consider the absolute value, absolute value of the series, the sequence. By the way, absolute value of series mean different thing you put outside. Okay, but now we are considering the sum of absolute value of the sequence. Okay, so put inside. Okay. Every term have to be positive instead of just the sum. Okay, but you know about this absolute sum or not? Sum of this absolute term or not? Do you know anything about it? It's still jumping around the course. Anyway, to relate to what you know. And think. Think, don't look at me, think. You relate to something that you know. No? It's quite close to 1 over n squared already. But can you relate them in any useful way? Squeeze. How to squeeze? You can squeeze, but can it give something useful? You can squeeze. But you squeeze just says what? The term inside here is less than equals to. It's bounded by 1 over n squared. Then you just show that this term will go to 0. But this term to go to 0 doesn't really tell you, right? This series can still diverge, right? Like harmonic series. So how do you determine whether this converge or diverge? Limit comparison test. So which series you want to compare? Well, maybe you can try it. So how about we just give us some spaces? So you say you want to do limit comparison test. So you want to compare to 1 over n squared like that. Okay. Okay, so let's try first. Let's do some working. What do you get here? Multiply it in, I think you can, right? So limit of n to infinity of 1 over cos n. Oh. So what's this limit? This limit diverge. Sorry. This limit diverge. Limit comparison test, what do you aim for? What do you end for? What's the statement? The L have to be what? The limit have to be what? If it is finite, then either they converge together or diverge together. If it is 0, then if Bn converges, then sum of An also converge. Okay. But this one diverge. Nothing to say. Easier. There's more easier tests you can use. Easiest one. The name content simple. Very simple. The name content simple. The comparison test one. Okay. Simple comparison test. So how to compare? Compare to who? So this one doesn't work. So we note that. Consider this. So note that. Still, okay, we will still play around with 1 over n squared. Okay, we know this. This is what? An greater equal to 0, less than equals to Bn. Then we can use simple comparison test here. How to use? If I know that the sum of Bn, the right hand side one, is convergent, meaning what? The sum of Bn and An also converge. Right? Okay, simple. Start with simple one first. Okay, so sum, since sum of equals to 1 to infinity of 1 over n squared converges by what? Same reason as before. This is a P series with P equals to 2, which is greater than 1. Okay, then by a simple comparison test, we know that the series of cos n over n squared is convergent. Okay, so since we know that the absolute of cos n over n squared converges, the series of this absolute term converges, meaning what? By absolute convergent test, we know that the original series also converges. It doesn't just converges, it must converge absolutely. Okay, absolutely convergent. Yeah, no. So don't restrict your imagination. You can combine a few tests together. Okay, in particular in your assignment question, you combine a few tests. You need to combine, not just one word. Okay, maybe obviously you need to start with tutorial question first. Try use one test to check conversion, and then assignment question is harder a bit. You need to use multiple tests to check to do it for some of them. When's the due date? Next week is it? Next Friday? Yeah, okay. You still got time. And then you can come for the office hour Tuesday, Wednesday. Okay. What? What? 庄子庄子. Hey, by the way, I got English translation. It's not just read the Chinese character. Okay. Yeah. Okay. Right. Yeah, so this is about absolute convergence. Any question about this absolute convergence? Okay, no. Okay. All right, so the other thing is about a rearrangement. Okay, this one I think we don't test it, but just quickly give you this idea first. So rearrangement. So you could imagine that within the series, right, you have a sum of terms. You can rearrange them. You can add them in a different order. Okay? So you might think, well, how this gives something interesting? Okay, how this gives something interesting? Maybe I don't write. I just jump to this fact here. I think we rarely test on this thing, but I want to give you an idea. The proof is quite long also. So there's a rearrangement theorem here, says that if, okay,
if the series you started with is absolutely convergent, meaning what? Test you definition. What does it mean by absolutely convergent? Both converge. So what both? The original series converge and also the series of the absolute term also converge. So if it converge, right, that means there's a sum there, correct or not? So it is a finite sum. Then the theorem says that no matter how you arrange the term inside your series, it still computes the same sum. I think this matches expectation, right? It shouldn't depend on the order. Because, why? Because sum is commutative. And then even no matter how you commute, one day you will reach that every number, I mean, all the number in the end, correct or not? Because you are considering n to infinity. So maybe it will appear at the later partial sum for that term, right? But second one is very interesting. This one is proved by Riemann. You know Riemann? Riemann's sum. Okay, Riemann. This thing is proved by Riemann. I forgot already one of the thesis. He says that if an is conditionally convergent, okay, and you can pick any real number, you can do something very cheeky. Okay, how is it? If you rearrange your an, you might get the sum equals to r. So there's some room to play here. Can you imagine what room you can play here? What does it mean by conditionally convergent? Say what? This an converge, but the series of absolute term doesn't converge. So can you imagine or not? What room you can play here? And this is very strong. There exists a rearrangement such that it has a sum equals to r. And then this r is any r. Negative million, 1 million, 2 million also can. For any conditionally convergent series. This is a very strong result, you know. 夸张你要什么号码它都可以给你。Do you know what room we can play here? What room? What's the difference between conditionally convergent and absolutely convergent? So the sum of absolute terms might not converge, right? So meaning what? So what does the absolute, like the modulus, remove? It removes the negative, correct or not? So there's a negative term to play around here. So how do we play around with the negative term? We can first arrange, this is the room for you to play, rearrange. You can maybe take a sum it up to r, or maybe a little bit more than r. Then what do? You can start to take negative term to bring it back to r. Maybe you add to less than r again, but you still got a positive term. Add again, a bit more than r, but you still got negative term again. Then you add it back again, less than r. And then you can go around r. And then you can prove that the result is you can prove that this converges to r. Okay. Actually, like the alternating series, but this alternating series is just plus minus plus minus plus minus, right? For here, you maybe can do plus 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 a bit, and then minus 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 a bit, and then plus 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 a bit, minus minus a bit. Then go around this r. And then Riemann proved that it's possible to converge to R. Okay. Yeah. This proof is not hard, but a bit long. Also, last topic in the MA. Not very important here.
maybe give you an example. Give you an example. Not very important, but give you an example to see what is really going on. Consider the alternating harmonic series. Okay, so we start with the sufficient condition of this theorem here. Okay, we have a conditionally convergent series. Since it converges, right, it must converge to something. Okay, I don't tell you how to compute this lone 2. Okay, suppose it equals to lone 2, or any finite number is fine. But what can you play around with this series here? So if you imagine, if you multiply half to this series, okay, and then add 0 between the terms, what do you get? You get this series here, 0 plus half plus 0 minus 1/4 here. Okay. Similarly, you do the 2 to the right hand side, you multiply half and then plus 0. So you get half log 2. Okay, what's next? What's next is you can add these two up together. Okay, add these two series together. For example, what? 1 plus 0, you get what? 1. Minus half plus half left? 0. Nothing. 1/3 plus 0 left? 1/3. And then minus 1/4 plus minus 1/4 minus 1/3, 1/2. And then you plus again. And you see that all these terms appear from alternating harmonic series with a rearrangement. Okay, you rearrange it. Can you see or not? So 1/3 comes to the front, and then you bring 1/5, 1/7 to the front, and then you add minus 1/4, and then you can see that all the term in the alternating series appear. But now you don't add up to lone 2. You add up to another real number. Okay. But the result is that you can put any number here, such that I can have a rearrangement of the alternating. Very strong result. Okay, if you are interested, you can try and explore in your project. Okay, any questions so far? So far, okay. Okay. Yeah. I think we won't do calculation on this thing. I just want to give you an idea. Okay, if it's okay, then we will continue with tests. I think how many more tests? Let's see. 2 more tests. We will say bye-bye to all these series tests. Okay, 2 more tests. 2 more tests. Huh? 2 more tests. Yeah, 2 more. Ratio test and a root test. Actually, it's counted as a very versatile test. Very versatile. A very useful one. Okay. I think after test for divergence, right? Ratio test is the next versatile test. So whenever you want to do this question, you should start with test of divergence first, and then you straight away test ratio test first. If doesn't work, only you go to the rest. Yeah. Okay, so let's do this versatile test here. Now, let me see, where's my blackboard? Do you know why I use black for my red screen? Don't use it in your assignment. Do you know why? I need to use red pen. Red pen on black. I know still can see, but it's harder. You know why? Later I need to submit your assignment for sample for the government to see. So it's better you use white black.
Right?
Huh? Private also need because this is the MQA, quality control, quality of MQA. So we need to submit your assignment, test, final exam to them. They need to do how to say, yeah, assessment, yeah, yeah. You know why I use black or not? It's like blackboard lah, digital blackboard. Hey, but what do you want to say? Oh, okay. Yeah. Blackboard, a digital blackboard. Instead, we have a chalkboard, but we just use a digital board. Huh? What? Okay, so let's look at this ratio test. So why is the ratio test versatile? Because we don't need to go and compare other series. We just look at the series we want to study. Okay, we just start with a series of must be non-zero terms here. So you need to be sensitive. Be sensitive. Whenever you see non-zero term, I say non-zero term, meaning what? I need to do some operation related to what? What operation must be non-zero? Sorry? Fraction, division, quotient. Okay, you cannot divide by zero. Okay, so we have to do something related to being non-zero. So meaning, what do we do? If what? If the limit of an plus 1 over an, okay, and then we take the absolute value equals to L, which is, okay, so there are three cases. I just summarize it. So, should I summarize? Let me think. Okay, never mind. I just stand it off. So this is equal to L. Okay, I summarize like this. So suppose this thing is equal to L. L, so L, if L less than 1. Okay, if L less than 1, then the series converge. Not just converge, or converge more strongly. Converges absolutely. So there's a reason why we consider this absolute quotient here. If this L greater than 1, okay, or this L is actually infinity, then the series diverges. But if this L equals to 1, the test doesn't tell you anything. You need to do something else. Maybe converge, maybe diverge. Okay? So think about, read this statement again. Okay, why does it make sense? Okay, why does it make sense? So what's this limit here? What is an plus 1 over an? What are you comparing with? You are comparing with the next term and the previous term. So if the ratio is less than 1, meaning what? This next term is pretty small compared to the previous term. Okay. Pretty small until that you can show that this series converges. Absolutely. This is the rate of decreasing that you need to make sure that your series converge. When you compare the consecutive two terms. But what happens if this ratio is greater than 1 or infinity? Meaning what? An plus 1 is at least as big as an. Can you imagine or not? What does it mean by at least as big? For example, 1, 2, 3, 4, 5, right? If you add these up, for sure, it diverges. Okay, so this is what they prove. But if it's equal to 1, then do you have example in your mind or not? Equal to 1. When L equals to 1. What example in your mind? An plus 1 over an equals 1. 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay. Maybe diverge, maybe converge. Okay. Not always diverge, maybe converge. Because not exactly equal to L, right? Because this is about limit. About limit. Maybe just to the end is equal to. So this is about ratio test. So let's see how useful is this ratio test is. So let's try some example. So for example, show that. Okay, no need to show, just look at the sequence. So let's look at the sequence here. Okay, so we want to check about the convergence of the sequence. So in this topic, whenever you see a series, there's only one thing you wanted to do. Ask whether this converge or not.
and then how it converge. Convert absolutely or conditionally. Okay, so these are the only questions you want to ask about series. So let's check using ratio tests. Okay, ratio test. So what do you need to do for ratio test? So what's your AN here? What's your AN here? Is it 3n over n factorial or not? Do you need the alternating sign or not? Yeah, do you need it? When you use ratio test, you regard the whole term as your AN. This is different from your alternating series test, because alternating series test, we take the alternating sign out. Remember? So let me write it down for you. We take the alternating sign out when we consider for AST. Okay? But for ratio test, you need to take everything. Okay? Yeah. Yeah. I haven't finished. I just want to set my AN first. Yeah. That will do. That will do later. Later will do. Yeah. Later will do. But you need to pick the right AN first. Okay? Okay. Otherwise, you are using different theory already. Okay. Okay. So what do you do for the ratio test? You simply compare the AN plus 1 term with AN. Okay, so what's the AN plus 1 term here? Minus 1 to the n plus 2, and then 3 over 3 to the n plus 1 over n plus 1 factorial. Divide by minus 1 to the n plus 1, 3 to the n over n factorial. That's all. So what is this? Like Jian Tong say, no need to care about this sign because we are taking modulus anyway. But can we do any simplification or not on the rest? What can we cancel? What do we left with? What do we left with? Can we cancel? What can cancel with what? 3n cancel with the n power. Okay, and then n factorial cancel with n plus 1 factorial. You left with n plus. You left with modulus of 3 over n plus 1, which is just 3 over n plus 1. And then you go back to the limit of sequence. This is what? Equals to 0. So which case do we have here? This is the first case we have. L less than 1. Okay, so this thing is less than 1. So by ratio test, this guy will converge absolutely. Okay? Okay or no? I think quite straightforward. Quite straightforward. Okay, let's do one more test, then we take a break. So next test is root test. Okay, root test. So root test. So meaning you need to take roots somewhere else. Okay, so where do you take the roots? So similarly, we start with a series of non-zero terms. Series of non-zero terms. What do we do here? We take limit of n to infinity of n root. Okay, can you imagine what happened if you take n root? An, absolute value of an. Yeah, can you imagine what happened to this quantity here? So is it obvious why we put an absolute value around an before we take root? No one. For example, square root of minus 1 is what? Complex. You need to take complex limit. That one different story. That one is a second year, second sem complex analysis. Not here. here we only do real analysis, real number. Okay, so we need to make sure the result we get the answer we get is real number. We only consider limit of real number. Okay, and then if you take higher power of root, what happens? This value will get smaller. Square root 2, cube root 2, cube root. But another interesting thing is this root is taken following the n term. So the first term you apply small root, the second term you apply square root, third term you apply cube root. Okay, turns out that this kind of sequence tell you something about the convergence of your series. Quite interesting, huh? But I won't prove it. Okay, so this L, if this L similar to ratio test, very similar. These two cases is these two tests is very similar. Just that the limit, the term of limit you take is different. Okay, if this L is less than 1, okay, you want to predict the series will what? Converges? Absolutely. Okay, and then if this L is greater than 1 or equals to 0, what happened? Similar to ratio test, the series will diverges. Okay, and if this L is 1, then the test is inconclusive. You don't know what happened. It's very almost useless, almost, but so the only thing you need to hope for when you use these two tests is the previous two previous two situation. Okay, you want to hope that this limit less than 1 or greater than 1. Okay, if it's equal to 1, then you need to try other things. Okay. It turns out that if root test work, ratio test will also work. Okay, this is true in general, but not the other way around. Okay, so people actually like root test more. Okay, but computational wise, I think ratio test better. Depend on your series. The example that we gave in this class should be ratio test better. It depends on calculation. But in reality, if root test work, ratio test must work. This can be proven in general. Okay, and then we will talk about this. Okay, so let's use this test. So you might think, oh yeah, what example can we compute n root? So we will make a tailored example also. So look at this complicated series here. So how complicated is it? So simply we add an n power to it. I think kind of stupid. So right, last time we just looked at, for example, 2n, the series of 2n plus 3 over 3n plus 2. Okay, but now I look at the growing power of them. If I hand you this, you also crack your head. But since I gave you the root test, you can cancel out the power. Okay, so you can cancel out the power. So what do we do here? So if we're gonna use root test, we just simply take the n root of 2n plus 3 over 3n plus 2 to the power n. Yeah. So this is really tailor-made one. Okay, but do you know that you can remove this absolute value or not? Do you know? How do you know you can remove this absolute value? Because what? Inside there is always positive, right? Because our n is greater than 1. Okay, whatever you do inside is positive. So you can simply just remove the absolute value first. Otherwise, you cannot simply take the root away, right? You cannot simply take the root away because maybe potentially you will meet a negative. Okay, right. But until this stage, I think it's pretty clear already, right? What is this? This is what? I don't want to write the step down. Maybe you write it down. What's the final answer? 2 over 3, good. 2 over 3 is less than what?
By root test, it is absolutely convergent. Yes, good. So these are very easy examples.
Just that I want to show you that what could possibly happen. What could possibly happen?
Okay, any question? I think we have finished all the tests finally. So yeah, let me show you a list of tests we've gone through. List of tests. Where's it? List of tests. Yeah. So there's a list of tests here.
Okay, if you want to do revision, what we have gone through, we have gone through test for divergent, T-series, geometry series, comparison test, simple comparison test, limit comparison test, alternating series, ratio test, root test, integral test, absolute convergence test.
All these tests, make sure you know how to use. Okay, make sure you know how to use. And then, what's the strategy I can suggest you here?
So whenever you got a sum of a series of AN, what do? First, use divergent test first. Test for divergent. If the limit of AN not equal to 0, then diverge already. Okay, throw the series away. If it's equal to 0, not sure. Okay, not sure, what do? Straight away go to absolute convergence first. If it's absolute convergent, then meaning what? It also converges. Okay, so you consider the sum of A absolute AN first. You can use all the tests to check whether this term converges or not. If converge, that means it's absolutely convergent. That's good. If not, still cannot decide. Still cannot decide. Maybe this series got pattern one. It's plus minus plus minus plus minus plus minus. If it's like that, then you can use AST. Okay, if yes, converge one. If not, good luck. Please look at the pattern of the sequence of partial sum. Check how it grows over. No question? Yeah, this topic you have to try more exercises. Okay, like the textbook one. Okay, then you will see how which test is better for which kind of series. Okay. And there's a list of revision question in the lecture also. You can try. Okay, try different way. Okay, try different way. If you get a better way, you can inform me. Inform me. He said I got a better way than yours. I mean, okay, shorter way. Okay or not? I will post out the all the solution for the revision question. Any question? No. If no, let's break until 10, 11. 1, 1, 1, 1.你这 max 手太低了，不要说去了，进来。04，2404，哎，对呀。熟悉的人在哪里来的？去哪里？去那边，那个。等下会给 ECA，然后拿去 SFS 接。就是 chop 这边了，不是这个就是这个的。那他妈是签完名啊，不是 chop 了，应该就是这个东西了。这个东西。刚上完。哦，你们比我们上完哦。我们上11点，上 MA 说，不知道怎么你们是提早，通常是一个时间的。对啊，是8点开始。是哦，你们提早。是啊，我们9点嘛。对啊，正常早八。其他的 MA 是9点的，还有一个 MA 是9点，MA one 9点。对，好像 Calculus One 我感觉也是9点过。那我们
你之前也是8点，然后8点的话是5年，不是你有没有拍出？对，好的。OK，拜拜，再见，拜拜，拜拜，拜。哎，跟我有时候看你的 note，为什么你这里比较写它的范围这样子，比如讲刀这样子？哦，因为我就是就是天然假设它就是 就所以一个是这样子。Yes，那个 notation 我应该有介绍之前，我有写。呀，如果没有特别的情况，这个就代表了。OK。呀，如果我有这样写，就要小心，因为有时候稍微2，有时候稍微3。对，你这个就假定是从 E 开始。Yes，E 再补 Yes。如果没有写，一定要重练。这是 notation，然后我需要特别讲，就是我有讲，在前面介绍这个因为这个我没有听到背景，但是我有写在那个 action note 里面，你要找回看一点，因为这个 action 很重要，但所以不一样的人用不一样的，因为就方便咯，反正每次到一个到一半容易记。但是我一写出来，其实要看它的 end 到底。那口碑，又去玩了。都可以看一下。
所以说是会有我觉得我在哪这本地方，因为都不一样的。没有，你现在是做 MAE 的东西，但是 MAE 的东西是在这也不是 MA2，就是跟 MA 是就是从 B 拿到 Real 和 Complex 那边的嘛，就是那里分白的有点 Real 和 Complex 那边的。也有过啊，有 Real 吧，我有一点，为什么？有吧？那有吧？有吧？还有。Yes，大个米，哎，在，这个点，他拍给你看的，他不在这玩，对吧？啊，我没有拍给你啊，没有啊，没有在玩水。你在做？你看，有没有那种？在所谓的年去嘛？有活力，有活力的这个动作之前在。是啊。但是我们刚刚传到这里面说你吃的，哎，你知道我跟做一个人，不是他是 retake 跟你们一起，然后他还有他的 replacement 还有一种是 MAE，
3点到5点。
哦，8个这样子
对啊，从早上8个小时，在 MAE
男的女哦，
不知道男的女啊，这男的
哦，还有 probability 啊，
不确定诶。
我这边都不是，
所以那个是好，我都讲不是啊，
还论那个水点是认错了，也就是他。
我那懂他变化这样大哦，
那是啊，知道是戴眼镜的啊，他有戴眼镜，
还是他变化很大，还有头发，他有头发，
我都讲是他的，
看到
一眼就认错了。
你们变化大了，
看到，
没有，主要是这个时候我就看到他一眼过来就追跟着现在，
做
下来
做下来多久了？
不对啊，
老啊老啊，多久？
还有4个小时。
还有连着4个小时要做的。
可是我
讲了吗？
讲啊，
那礼拜一就讲了，
上个礼拜有讲了。
他随便摆一下子就杀掉了，
拜一。
还有一样，
而且
有
没有印象啊。
哦，
所以在哪里？
他在热搜手写，
在哪里啊？
什么写？那厕所我在上厕所。
谁讲的？
在 A4G05。
哦，A 是0，OK。
啊，
你的班有多少人呢？
看见我，要他给你玩，碰不到我，
存在感比较低。
你都笑到上课我。
那笑最靠我的一点恐怖的架头出来，
加一点，好像笑这来，
哎，你看他今天会不会在讲大声的？
他没有，他没这样，
那个是你的底缝哎，那他底缝，底缝。
再看他今天会不会在讲？
内涵我们3个小时考，
已经被他们 Excel
每一堂课在内涵。
因为我们记得不教室里，我们想说不
因为3个是4个 S，你说我们3个嘛，
我连把
反正我全部
那把我想当做是评委假期啊，
然后3
不是，
他就在就是吐槽我们用10个在那边做，
不是吐槽一个事情吧？
而且是全班都用10个。
你们记得你们吃过没？我没有印象，我有做过那种手会。
那你是教过是吗？
证明说你是对的是吧？
就是你考过的是什么东西我都不记得，然后他突然间讲，你们为什么要用10个，不是3个就够？我就想，我有吗？
你们，
你记得我是哪次吗？10个啊，我大概6、7名。
他死命拿
你有多拿纸，可是我没有拿纸，所以我不知道我有没有。然后他就来引上我，他在你们就
哪个？
他不是以前让你，他是引上去
是什么谁让他掉？
包括我，
哦，对，我一个丢人嘛，我跟他讲说第几，他的来选我第几名，然后他也讲，他们
哦，
对，
那个老师有一个还是你讲一下，然后他是把这个
我今天迟早
有个人跟你开，
迟早会，还没有到一个等级吧？
我就把丢人拔出来。
那个啊这边，你们班好像有一个人在考试题里面写一个，你们连 lecture notes 里面的第几页出来，
他讲
3，老师这个要说他写错了，差2遍。
对
写了很多自己写错了。
对，我听到让我想到审计了。
后来我们
他那个成绩已经是超乎我的想象了，被吓到我就拿了。
OK。Okay, ready? Last hour. Last hour. Okay. So we're gonna do new stuff now, okay? We're gonna do new stuff. Still series, but we add in variable this time. Where we add in variable this time. And the way we add it is very specific. Okay, so how we add the variable in, we use power. Okay, this is called power series. What's power? Power here is not Power Ranger. It's taking power of some variable. Okay, so definition. A power series, okay, involve a variable x. Very specific one about x equals 0. Okay. is a series, obviously. Okay, but how do we introduce the power on x? So we will take sum of Cn, n equals 0, from n equals 0 to infinity. So be careful here. We start with 0 now. Okay. Cn times x to the power n equals to C0 plus C1x plus x squared. Cn times x squared, C3 times x cubed, and then so on. Such that what? Where these Ci's are in R, actually. Okay, so these are just real number. Oh,
Okay, so meaning what? We consider power of n. Okay, and we add them up. Not just that, we can alter the coefficient. Okay, alter the coefficient. So it's like you adding these monomials together.
so you first, what do you do? What happened in this series? You start with what? Constant term. Okay, you start with constant term. And then second is a linear term. And then quadratic term, and so on. Okay. Does that make sense? Is it quadratic? The third one. Yes or? Yeah. Okay. Yeah, so this is called a power series. Okay, power series. Okay, so this is power series. So for example, a very quick example is if you look at this series here, so just simply take Ci equals to 1, the easiest one. Okay, so meaning we take 1 plus x squared plus x cubed plus x4 and so on. Okay, we can ask when this series converge. Okay, when is it converge? So this one converges for what? X. Okay, so if it converge, what is the sum? Converges, what is the sum? Okay. But isn't it this seem very familiar? This seem familiar or not? Seem familiar? Geometry series. How does geometry series look like? Huh? What's the geometry series statement? Recall some of what? A, R, N, and then N from 1 to infinity. Again, we write it out purposely. Then converges if and only if absolute of R is less than 1.
So, so geometry series is more general than what we look at here. Correct? Can you see or not? Why is it more general? In our example, what is A? Hey, did I write wrong or not? Is it Rn minus 1? Rn minus 1, right?
Should be Rn minus 1. So if you look at the
First term here, what happened? This first term is A, but the first term at the top is 1. Alright? How about the second term in the geometry series? AR, AR. But here, just X. So A equal to 1 again. Okay, so you simply take A equal to 1, it reduces to this case. I just replace X by R. Okay, and then what other things I replace? I start with 0 there. Because you can see that the power there start with n, but the power here start with n minus 1. So if you place 1 into here, actually you also start with 0. Okay, no? So it's really a special case of geometry series.
So what? So we would say that so by geometry series with a equals to 1 and r equals to x, we know that the series converges only when the absolute value of x is less than 1.
Actually, this is not a coincidence why we want to change R to X. Previously, I want to view the R as a ratio. Whenever you see X in calculus, what you want to imagine? Real function, real value function. And later, we will see how we relate this sum to a real value function. And later. But for now, let's keep it in this way first. So what's this sum? Do you know this sum or not? What's this sum? How to compute? The sum to infinity, right? What's the formula for sum to infinity? You take the first term divided by the ratio, one minus the ratio, which is x in this case. Okay, so in this case here, what do we obtain here? So if we write the sum out, is 1 plus x squared plus x cubed plus x4, so on. This is actually 1 over 1 minus x. Okay, so what do we do here? So first of all, if you study calculus, right, this summation notation and this expand notation, right, you need to be able to quickly switch between them. Whenever I write this down, you need to appear this image in your mind. Once you see this image, you should know how to write the summation formula up. Okay? And then the other thing is, you can see here, this is a sum of infinite term, never ending one. But this one, we call it a closed form. It's closed. Why is it a closed formula here? Under this formula, right? What do I need to do to evaluate? I just substitute x. And then I take 1 minus it and then inverted it. But on this side, what do I need to do? I need to compute x, compute x squared, compute x cubed, compute x4 for infinitely power of them and then add them up. Taking power is not a problem, but adding infinitely many terms up is a problem. But turns out that this formula tells you how to do everything. Okay. So this is very important. Only when x, absolute value of x is less than 1, you can do it. Other cases, not sure. I don't know. Maybe diverge. I think it's diverge, right? Because we prove if and only. So it must diverge at other places. Okay. Only in these cases you got this closed formula. Okay. So let's look at more series now. So look at more series, power series, I mean. So what kind of power series? So you can imagine that what trick you can play with power series. The only trick you can play with it is you play with different coefficient. Okay, because power series for the power of the monomial is fixed already. So the only thing you can play with is the coefficient. Okay, so let's play with different power series with different coefficient. So how about this one? So sum of Sn over n plus 1 to the power n. Okay, let's look at this one. So what's the coefficient here? So this coefficient here is simply 1 over n plus 1 times 2 to the power n. Okay. So to swap between the summation notation and the expanded sum, we can see that what's the first term here? What's the first term? 1. What's the second term? You quickly compute or not? Jason, what's the second term? Can see, you know, see?
2 to the n is it? What's the second term? Over 4. Maybe we can leave it unmultiplied, so 1 over 2 times x over 2, right? Okay, how about the next one? 1 over 3 times x square over 2 to the power 2. Okay, and then so on. Okay. So can you see whether this converge or not? Can you see? Not sure. Okay, so what kind of what kind of test we can try here? What test we can try? Ratio test. Okay, we can try ratio test.
Because what's the indication you can do ratio test? You can see that these terms are defined by n.
Okay, you can try it. So by ratio test, what do we expect here? When does this series converge? The series converge if the limit of n plus 1 term divided by an is less than what? Answer. Less than what? Yes. Okay, so let's check it. So note that our term here involve variable x, but that's fine. That's okay. No problem. Okay. Well, what's the cancellation you have here? Sn will cancel, right? So let's cancel it. And then what else cancel? 2n also cancel. I think that's it, right? So what do you left with? So if you wanted to converge, the following inequality have to be true. N plus 1 over n plus 2 times x over. Okay. We can go further a bit. Okay, we can go a little bit further. So we can try and pull these n plus 1 over 2 times n plus 2, the scalar out. Okay, we can pull the scalar out. Okay, so we need to make sure that this is true. Okay, so, but to make sure this is true means what? Means what? Means what? Means what? What is this? Can you compute the limit here? What's the right-hand side limit? Sorry, left-hand side. Right-hand side is just 1. What's the limit of this left-hand side?
How to compute this limit here? What are we doing here? So this scalar depend on n. How about this x? Does it depend on n or not? It doesn't depend on n. But how do you build this x? It should be fixed. Some other number. It's some other number. So the thing that you take limit is just this scalar part here. But do you know how to take this limit here? So when you look at this limit, this x becomes scalar. Okay. So there are actually two variables here you need to take care. One is x, one is n. Okay, but when you take limit with respect to n, x become a scalar. Okay. So what's this limit here?
Is it converge or not? Converge or not? So let me write further. Remember how you compute the limit? So you consider 1 plus 1 over n over 2 times 1 over 2. Right. Does it converge?
1 over n converge to 0, right? 2 over n converge to 0. So everything inside here converge. This one scalar, 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 converge, scalar, converge. So you use the property of convergent sequence. So you bring limit to every one.
Yeah, but if you bring limit to everyone, what do you get? You get absolute value of x times 1 over 2. So this means that you need to make sure that what? 1 over 2 times x, absolute x is less than 1. Only you can use ratio test to conclude it converges. But this means what? This means that this absolute x has to be less than 2, which means that your x has to be in between -2 and 2. Okay. Okay, good. But what happens if this limit equals to 1? Ratio test says what? Inconclusive. Inconclusive means what? Maybe converge, maybe diverge. So still have possibility to converge. What to do? What to do? You need to check at those points. Okay, you need to check at those points. So when does this limit equal to 0? When does this limit equal to 0? Sorry, equal to 1. If you replace all the inequality equals to 1, meaning what? X might be equal to -2 or 2. So these 2 points you need to check separately. Because ratio test doesn't tell you. Correct or not? Ratio test doesn't tell you at this point. Inconclusive meaning maybe converge, maybe diverge. So you have to really confirm whether it diverge or converge. So you need to check on those points. Okay, so now we will check. So we still need to check x when x equals to -2 and x equals to 2. Okay, because the ratio test is inconclusive there. Okay, so let's check it. So you can see that when we replace variable s with a specific number, our series become what we have been studied before, because all of them are just in terms of n and number, rational number. So if we replace this by -2, what do we get? This is -2 to the power n over n plus 1 times 2 to the n. Okay, but what is this? This is just the series, alternating series of 1 over n plus 1. Do you know whether this converge or diverge or not? Why? Why converge? Why? What did you say? What did you say? But harmonic series also go to 0, right? But diverge or careful, not just limit an have to go 0. Something else need to be true. Yeah, alternating series. Okay, true alternating series. But this guy, you should know what is this. List it out. List this guy out. What's the first term? First term is what? Answer. 1. What's the second term? Isaac. What's the second term? Huh? What's second term? Yeah. -1 times over 2. Third term, 1 over 3. Fourth term, what's this? Alternating harmonic series. So actually you can rewrite this sum, right? Actually you can rewrite this sum by starting at 1, which is -1 to the n plus 1 times 1 over n. Correct or not? If you push your n forward by 1, meaning you actually this one need to push backward. Push backward your formula by 1. Okay, so exactly this is alternating harmonic series, which we have shown that it converges by the alternating series test. Okay, if you forgot, then you need to redo the alternating harmonic series test. Okay, if you remember, then you can say that, oh, this is the alternating harmonic series. Okay, how about the other cases? Okay, how about the other cases? So the other cases should be similar, right? We just have what? Can you imagine or not? What's the other cases? When x equals to 2, what happened? Even easier, or correct or not? No more alternating. Can you imagine? So if I remove this 2, okay, let's remove this way. So if I make it positive, I make it positive here, then what happened? Seriously, I don't have the alternating already, alternating series sign. But without the alternating series sign, what's this? How many series? So it diverges. So it diverges at the other endpoint. So it diverges at the other endpoint as it is a harmonic series. Okay, so altogether, what do you say? So you can say that this series starting from 0 converges on x in, or let's say converges at x in -2 inclusively up to 2 exclusively. Okay, is it clear? Clear now? So you can see this series with what? With this series with variable that converge for a range of x. Okay, for a range of x. For what kind of range you could get? So let's look at different example. So let's look at this example. So how about sum of xn over n factorial? So what can you see here? What is the coefficient for your power series here? What's the coefficient? What is the coefficient here? 1 over n factorial. Okay. So what are you imagining here? Your s, the power of x remain the same, but coefficient make difference here. So how does n factorial grow? Pretty fast. Okay, what is 1 factorial? 2 factorial? 3 factorial? 4 factorial? 24. 5 factorial? 24 jump to 120. 600, 6 factorial? How many thousand? 700. Still 700. Okay, 100 jump to 700. And then can compute more. What more? 7 factorial, x factorial. Okay, so it increased pretty fast. But you put it in the denominator, meaning what? You make the whole term smaller. So even smaller, even smaller, even smaller. Okay, so do you hope that this series converge or not? You should hope, right? Because it decreases quite fast. Okay, let's see how fast this term decreases. Okay, let's see. So we use the same technique here. We will use ratio test again. See when these series converge. So, because ratio test will give you some useful inequality. Okay, so we will use ratio test. So we want to make sure that an plus 1 term, the ratio between an plus 1 term and an is less than 1. Okay. But if you compute this limit here, what did you get? You simply get the scalar x times 1 over n plus 1. Less than 1. What happens here? What's this limit here? So what's this limit here? So I want to write this down. So what's the left-hand side limit here? What's this left-hand side limit here? What's this limit? Scalar times 1 over n plus 1. It is 0. But 0 is always less than 1. Correct or not? So meaning what? What does it mean? No matter what x you put in, no matter what scalar you put this in, the left-hand side here is always 0. So meaning what? Meaning that this implies that and the series Sn over n factorial converges for all x in R. Because no matter what x you put in here, the left-hand side limit is always 0. And 0 is always less than 1. So by ratio test, your series converges. Converges everywhere. Okay, so this is what we call converges everywhere. Okay, so even you put x 1 million here. Okay, 1 plus 1 million, 1 million to the cube, square, 4 power, 5 power, 6 power, 7 power. If you manage to divide them by n factorial correspondingly, it will converge. It will converge. Okay, does it make sense? Okay. Okay. Okay, so this is another range. There's the other type of range. Let's see. So we have two type of range. One is interval range. The other is the whole real number can converge. So we have seen this type. So this type, let's look at this type here. So this type is the other extreme. Instead of divide by n factorial, I multiply. Maybe you ask, wow, grow so fast already, still can converge, man. Is there any x for this guy to converge? What do you think? What do you think? And just I argue for you, right? N factorial grow pretty fast, right? But is there still a possibility for this series to converge or not? Any s you want to try? Does there exist any s for it to converge? Only 0. Because 0 plus 0 plus 0 plus 0 plus 0 plus 0 is 0. Okay, so we need to prove it. Okay, how to prove it? Because you only know that maybe if you put S0, it converges. But how do you argue that for other cases diverge? Okay, so we have a good tool again. What's the good tool? Ratio test. Okay, so this is a very good tool to use. So by ratio test, when does it converge? The series converge only if the limit of the n plus 1 term over n term is less than 1. Okay. But what's this calculation here? What's this left-hand side limit here? This n plus 1 times s, right? Okay. So you want to make sure this less than 1, which is impossible unless s is 0. Correct? If s is any scalar that's non-zero, this limit is infinity. But when s is 0, this limit is 0. Can follow? Understand? Okay, so since I would say that the sequence diverges, okay, it follows that the only thing we can put for x is 0. Okay, but absolute x equals 0, meaning x is 0. This is a very special property for x for real number. Meaning if your real number length is 0, only the point 0 will have length 0. But this is not true in general, in particular in the general relativity. In particular, in the universe we live in. Okay, there might be some non-zero element that has length 0. Okay? You will learn it maybe in general topology. You can see these items. Okay. Yeah. Okay. Right. So you conclude that. What do we conclude? So we conclude that only when x equals 0, the series converges. Okay. Only when x equals 0, the series converges. Okay. So what time is it? Let's see what else we can do. Okay, I think we can finish out this section here. So what can you see here? So we can have a theorem here. So we have a theorem. So this theorem also can be proven, but we won't pursue the proof. So there's really only these three types. Okay, there's only these three types on which the power series will converge. Okay, so this power series is about Cn times Xn n equals 0 to infinity. Okay, converge. There's only three types here. So the first type is a single point. Okay, single point, which is exactly at the point of origin. Okay, this origin is very interesting. Remember just now we defined the power series above x equals 0. Okay, so they are related. So either it converges at that point x equals 0, or it converges on an interval. Okay, interval. So this interval here, right, it might be closed, might be open, might be half closed. Half closed is equal half open actually in this case. Okay, but either endpoint you can include. Okay, so possibly with endpoints, and or the other case is the whole real line on every point it converges. So really, the game we play for power series here is the Cn. What kind of Cn we can put? Okay, what kind of Cn? So in this case here, okay, we will define some terminology. So we'll define some terminology here. So we'll define that the L, okay, L above is called the radius of convergence. Okay, radius of convergence. Can you imagine why is it the radius? When you talk about radius, it's like circle, right? So if you talk about circle, you need what? You need a center. Okay, so what's center here? The 0. Okay, center around 0. So you can see that this interval here, if you center it around 0, what's the radius? It's exactly L. And then another thing to observe here, this interval is symmetric around 0. It's from minus L to L. Correct or not? It's not like 2, 3. It's not like minus 1, 2 like that. It's always minus 1, 1, minus 2, 2, minus 3, 3 like that. It's symmetric. So that's why we can define this radius. Makes sense. If let's say an interval minus 1 to 2, so what's the radius with center 0? You want to pick 1 or you want to pick 2? Don't know. Okay, so you can see that this theorem is quite strong. This interval is always symmetric around 0. Okay, symmetric around 0. So in this case here, we can we can maybe put remark. So we can remark that. So the first case meaning what? The radius is what? What's the radius if only converge at 0? Only 1 point. Exactly at the center. So what's the radius? 0, not extended from the 0. If it is an interval around 0, what's the radius here? Because this is symmetric, it is exactly L. Okay. And whole line, what's the radius around 0? Too long, cannot measure already. So we call it infinity. Okay. Yeah, another terminology we introduce, then we can go home. So The one is oh, you cannot go home. I can go home. Sorry. Okay. Okay. So we define the interval of convergence. Okay, of a power series is the interval, exactly the interval that contain all value for all value of x for the series to converge. For the series to converge. Okay, so let's go back to the tree type again. So if you can converge, if you only converge at one point, what's the interval? Okay, interval is what? How to define interval? So in mathematics, the definition only consists of two types. You need to understand. Mostly two types. One is about set, okay. The other is about function. Only these two main things. That's why you study in your discrete math set function. Okay. So interval here should be defined as a set. Okay, set of things. So what thing? Set that contains all values of x such that it converges. But the first case, it only converges at one point. So this set contains what? Only 0. Okay. Second case, what could happen? It could be open interval minus L or L, or we can include the endpoint. So how many possibility here? No lah, 4 only. I mean, L could change, yeah, infinitely families, but if you consider one type of L, there's really only 4 of them. So either half close minus L, half close on the left, or half close on the right, or close on both sides. Okay, remember just now we check the endpoint. Okay, check the two endpoint. If it converge, then we include it in. And then the last one is what? Last one is just R, or maybe sometimes you write negative infinity to infinity, like that. Okay. And what? And hey, where's your class? A4. Also, you guys need to move. Can we go a bit further before you move? Less than 5 minutes. Less than 5 minutes. So in general, what happened? Just now we just defined our power series at 0. So we can actually define power series at any center. Okay, at any center. So at about power series about any x. Let's call it A. Okay, that point A. So what do? I do shifting. Okay, do you still remember shifting in your function? Where you just take x minus A, shift it to A. Okay, so how does it looks like? So you have C0, C1 times x minus A, and then C2 times x minus A, and so on. And all these discussion will hold. So how does it hold? So you change your center to A now. Okay, and then what happened to the interval? You also shift your interval to A. How to shift interval to A? You simply add A to them. So you can plus A. So you will plus A on both sides. Okay, but if you want to shift whole real line again, what do you get? Again, the same whole real line, no? Okay, so it doesn't change. Okay or not? So in the end, what happens here? Radius wouldn't change, right? We just change the center. But the description for your interval of convergence should change because you already changed the center. Okay, so you add A to all of them. Okay or not? Okay, you add A to all of them. If you add A to this whole real line, obviously still the same line. Okay. Okay, so you need to be aware of two types of power series, whether it is centered at 0 or shifted to some position. In the next class, we will say why this shifting makes sense. Okay. Any question before we break? Finish, sorry. Okay, if no question, will see you next week.
我不要去本地嘛，我不要去本地嘛，3点我们得去吃早餐，
这样
对吧？
3点我们可以去吃晚餐了。
啊，要输班了，找空兵了没？
讲真的是讲假，
下
下礼拜
要不然我们到古都啊，还要讲
OK
要不然我们去古都一次。
可以啊。